In the previous video, we saw absolute and relative moves, where you could tell the motor to accelerate to some velocity, hold that velocity until it got close, and then decelerate and come to a stop at the final intended destination. Since this is velocity and this is time, the area under this curve is the total distance moved. We learned that you can iterate that move and/or dwell, and then jump to any other index. And you can keep adding any of the 64 possible indexed moves till your heart's content. Blended moves are the exact same thing, except instead of decelerating to a stop, when the final destination is reached for each move, you immediately transition to the next index without stopping. So you're blending or merging two or more indexed moves so you don't have to wait for the motor to stop between indexes. Let's do an example of that. I'm starting with the exact same setup as we had in part 1, so I'm not going to repeat that configuration here. Watch part 1 if you need to see how to do that. I've already set up a simple move with no blending. It goes some distance at this speed and accelerations, iterates 3 times, dwells for 500 milliseconds, and then jumps to index 1. Index 1 moves 4 times as far at 4 times the velocity and 10 times the accelerations, and then stops, just to give us some variety. I also set up the scope to monitor the velocity command. Make sure the drive's enabled, start the scope, and watch the slide as I toggle start. We get the 3 iterations of index 0, the 500 millisecond dwell between indexes, and then we see the faster accelerations of velocity of the single iteration of index 1. And we see the same thing here. The 3 iterations of index 0, the 500 millisecond dwell between the indexes, and we see the faster accelerations and velocity of the single iteration of index 1. And again, the sum of all these areas is the total distance traveled. These are standard relative moves. Now let's go back to the index editor and change index 1 from a regular relative move to a blended relative move. That is, we want index 1 to blend or merge with the index 0 move. Now remember, while this change was written directly to the drive, it was written to volatile memory. If you want the drive to remember the change after a power cycle, then be sure to also write it to the non-volatile memory. Now I set index 2 to be an absolute move back to 0. So let's toggle the second index selector bit to tell the drive to send the carriage back to the starting position. Toggle start, and the carriage moves back to our 0 position, giving us some room to work. Turn off that index bit so the drive starts at index 0. Back to the scope. Start the scope, toggle start, and stop the scope. Interesting. We just see one iteration of index 0, even though we didn't change the iteration count, and it didn't decelerate to a stop and dwell before executing index 1. It just transitioned directly into index 1. So when you're doing a blended move, the iteration count and the dwell time in the previous index are ignored. The blended move is great for those times when you need to wind up a spool of material rapidly, for example, but you need to slow down when you get to some length to prevent the material from bunching up or to give some operation time to run. Another common move is registration. Maybe you have some object placed randomly on a conveyor and you have a sensor detecting the edge of the object. We call that registering the object. You usually want to go fast between objects to save time, wait for the registration mark, and then go to some slower speed for accuracy, and then stop at some predetermined distance so when the move is in a new position, some other operation can cut or punch a hole or stamp, etc. So let's pretend we have a registration sensor coming in on digital input 10 so we can use this digital input dialog to control it. And let's do this registration move in index 3. I have this set up to do a relative registration move, 1 million user units or 50 millimeters on this slide at a slower speed so we have time to react in our demo, and some reasonable accelerations. When the drive sees the registration signal, it'll go another 10 millimeters at a quarter of the original speed. And none of this matters because we're stopping after this move. Now I'm going to do this twice. First, we'll run this index 3 move and we won't toggle the registration signal. In that case, this should run like a regular relative move that goes the full 50 millimeters and stops. Then we'll run the registration move in index 3 again, but while the carriage is moving, we'll toggle the registration signal and we should see the carriage slow down and go another 10 millimeters and stop. Here we go. Switch over to the scope. I already set up the registration signal and the imposition signal on our scope, so let's enable those. Turn on this index selector bit to enable index 2 and toggle the start to move the carriage back to our origin. Enable index 3 where we put our registration move by activating both of these index selector bits. Start the scope, start the move, wait for it to finish. We see the carriage slowly moving the full 50 millimeters, and stop the scope. I'm going to use my left mouse button to drag this lower area of the scale to the right to get everything on the screen. We see the motor ramped up to speed, held that speed, and then decelerated to the full 50 millimeter position. We also see the in position signal tell us the move is complete, and the registration signal did nothing. Again, the area under the velocity curve tells us the total distance traveled. Of course, we could have displayed the actual position, but I left that off to keep the display uncluttered. Let's select Index 2 and toggle Start to get the carriage back to our starting position. Go back to our registration move in Index 3, start the scope, toggle Start, and while the carriage is moving, I'll toggle the registration signal. Wait for the in position signal to tell us the move is complete, and stop the scope. I'll drag the scale with the left mouse button again to get everything back on the screen. We see the original relative move start its 50 millimeter journey, but when the registration signal toggled, telling us we found the edge of the product, the speed reduced, the carriage traveled 10 millimeters, and the move stopped. Your PLC could then use the in position signal to tell it to do the next operation. So that's a typical registration move. You have the system go fast until it finds the edge of the material or a registration mark of some kind, then it slows down for some known distance so you get a good, accurate positioning for your next operation. There is one catch. If you get multiple registration signals before the registration distance finishes, maybe you have some noise on the lines or get some chatter or switch bouncing like this, the registration distance will get pushed out to align with the most recent registration signal. So make sure the registration signal into the drive is clean and reliable. Well, that ought to be enough to get you started with blended and registration moves. In Part 3, we'll look at the dedicated moves the drive has to make your life easier when doing rotary operations. Meanwhile, click here to learn more about the LS Electric servo systems. Click here to learn about Automation Direct's free award-winning support options, and click here to subscribe to this YouTube channel and click that little bell icon so you'll be notified when we publish more videos like this one.